Hello everyone. It's been a while since I've done an episode, I think at least 4 months. But today I'm happy to have as my guest mathematicians Vicky Neale. She's the Whitehead Lecturer at the Mathematical Institute and Balliol College at the University of Oxford, and she was awarded the Mathematical, Physical and Life Sciences Teaching Award in 2016, and another award for being the Most Acclaimed Lecturer, again in 2015. And I also can confirm this from all my friends from Oxford. I mean, everyone absolutely loved Vicky. She also wrote 2 books for general audiences, Closing the Gap, a book on number theory, and Why Study Mathematics, whose subject matter can be guessed. And I want to mention that I know at least one person who fell in love with number theory after reading Closing the Gap, and now she's doing a PhD in number theory in the UK. So yeah, your book has impact. So today I'm gonna focus more on why study mathematics, but if time permits in the end, I might ask some questions about number theory and closing the gap. So, I mean, I just introduced you, but can you please tell us more about your mathematical background and why did you choose to study mathematics? I mean, are the reasons that you suggest in the book the same reasons that you had when you were young and chose to study mathematics?
Well, firstly, that's a very kind introduction. Thank you. And it's a great pleasure to be talking to you today. I really enjoyed maths at school all the way through. From when I was really quite little, I've always enjoyed maths. And for me, it was quite a natural decision that I wanted to do maths at university. And I was very fortunate that I ended up studying maths in Cambridge. As it turned out, for quite a long time, because I was an undergraduate there, and then I also stayed on and did my PhD there. And then, in fact, I worked in Cambridge for a few years at Murray Edwards College and in the pure maths department before moving to Oxford a long time ago now. It seems like a long time I've been working in Oxford. In terms of why did I choose to do maths, my main reason was that I really enjoyed it, and I had no clear vision of where that might take me career-wise when I was 17 or whatever, and making these decisions. It's been quite interesting as I've gone through my career working with young people who are doing their degrees, who are exploring, do I want to do a maths degree or should I choose something else, when I meet people at open days and so on, and then being alongside my students as they go through their degrees, and perhaps they arrive with quite clear ideas of what they want to do and they go on and do that, or perhaps their ideas change quite a lot, or actually I think quite a lot of them don't really have particular career plans when they start. They've chosen to do a maths degree because they enjoy maths, but also because of its versatility, because doing a maths degree opens lots of doors. And so one of the things that I wanted to kind of convey in the book, Why Study Mathematics, is how many career opportunities there are for maths graduates. I think sometimes it's not obvious what you might do with a maths degree. If you study medicine, it's sort of clear that you might want to become a medical doctor. If you study law, it's sort of clear you might want to be a lawyer. If you study engineering, it's sort of clear you might want to be an engineer. But what does be a mathematician mean? Is that the only thing you can do with a maths degree? Well, actually, there are loads and loads of things you can do with a maths degree, some of which rely on the specific kind of maths content that people learn in degrees, but often it's more to do with the thinking skills, those kind of transferable skills that employers really value. And so there are lots of options. So for me, it didn't really feel like a decision to do a maths degree, if I'm honest, but I know for lots of people, it's a really important decision. You're committing to maybe 3 years of your life, maybe even 4 years, 5 years. So it's important to get that right. And I was really happy when the publisher, London Publishing Partnership, got in touch with me about this series, because I think it's really important that people can make informed choices about what they do. So having information about what it might be like to study that subject, but also career opportunities beyond that.
Right. So when you started the plan to write this book, did you feel that in the British schools or something there are some misconceptions about the mathematics career and mathematicians, or did you just want to put together a resource for interested students that don't get to access this information in school, but not necessarily that there are misconceptions floating around?
I think that's hard to tell. I think often there's not very much information readily available, or it can be hard to know where to look to find that information about what might it be like to do a maths degree, or where might a maths degree be able to take me in the future. And obviously some students are in schools and sixth form colleges where they have teachers who are able to give them those kind of insights, but that's not possible for everybody. So I think it's really important that everybody should have access to that, regardless of their family background. You know, maybe they're the first in their family to go to university, maybe they don't know anybody who's done something like a maths degree. So making that information readily available. And I hope that the book will also be useful for teachers. Because lots of maths teachers who are fantastic maths teachers didn't themselves study a maths degree. Perhaps they studied engineering or physics or something altogether different. And they're really well equipped to be maths teachers, but they can't necessarily draw on their own insights. And also, there's a really big variety of maths degrees in the UK. You know, it's really interesting when you look at the university landscape across the UK, how many different flavours of maths degree there are. I think that's a real strength of our higher education system, that there are degrees that cater for students with different aptitudes, different interests, different priorities. So even if you're a student with a teacher who did a maths degree and who can give really insightful information about their experience, that's still only one type of maths degree. And actually there are lots of other kind of maths degrees out there, and it can be hard to kind of navigate that. So I wanted to try to help students, but also teachers maybe have some of that information through the book.
I also want to show the book to people. I mean, I ordered it last week, and this was my weekend reading. Well, after I read the book, I hope I won't disappoint you, but I was a mathematics undergrad years ago as a third year, and I dropped out to study something else. So perhaps I should have had this book back then, but yeah, I don't mind. I mean, I eventually ended up studying computer science and philosophy, and now I'm doing logic, but in the philosophy department, so it's kind of close. But I didn't.
It's all kind of joined up, right? I mean, we have to have these artificial divisions between subjects for degree purposes, but the boundary lines between maths and computer science and philosophy, logic and so on all seem rather blurry to me.
Yeah, especially logic. I mean, I feel myself in all departments and in no departments at all times, so it's quite weird. I mean, I have another question about studying mathematics. I mean, do you think that the good reasons for studying mathematics are timeless? I mean, for example, suppose you wrote this book 50 years ago. Do you think a person with your expertise would have written a similar book 50 years ago compared to today?
That's an interesting question. I'll break this news to you gently. I wasn't around 50 years ago. I certainly wasn't writing books 50 years ago.
I know, but
I think a lot of it would be similar. But I think that the changes in technology and the kind of, I mean, we're just talking about the links with computer science. I think the pace of change maybe has been dramatic in the last 50 years. And that has an impact both in terms of what students study in a maths degree, but also what they go on and do afterwards. And one of the things I was really conscious of writing the book is that a student who's maybe coming towards the end of their school career now, who's reading this book, who's thinking, would I like to do a maths degree? They're still going to be in their working life in 40, 50, whatever years time. And I don't really know what the world's going to look like in 50 years time, because society keeps changing, technology keeps changing, all sorts of things evolve. So one of the things that I think is a real strength of a maths degree is its versatility, not only in terms of what you do directly after you graduate, but also having the skills to be able to continue to adapt subsequently in your career. Some people finish their degree, they go straight into a job, and they stay in essentially that same career throughout the whole of their working life, and they progress and become more senior or whatever, but other people will shift and change direction really quite significantly. And it seems to be one of the strengths of a maths degree is that it equips people to be able to do that, to adapt. It's not a specific training in one particular job. It's not that kind of degree typically, but it gives people the tools and the skills to be able to adapt and evolve. And I guess, and you were asking, would I have written the same book 50 years ago? Well, I guess the last 50 years have really highlighted that versatility and the way that maths is now being used to handle big data, to do exciting things in healthcare and studying climate change, for example, where we have these massive amounts of data that we then have to analyze and make sense of in order to draw any conclusions. It would have been hard to predict 50 years ago that those were the kind of things that mathematicians might be doing. But in terms of, from the point of view of somebody who's thinking, do I want to do a maths degree, whether they're 17 thinking sort of coming towards the end of their school career, or whether they're later in life and thinking of studying as a mature student, I guess the reasons for doing a maths degree probably haven't changed so much. So people who like maths, who feel that they're making successful progress in maths, people who would like these kind of interesting diverse career options.
I mean, your job is one of a pure mathematician. Do you think that your job is shielded and safe from future developments in artificial intelligence, or do you actually think that the job of a mathematician is in danger, or potentially?
Yeah, that's a big question. My job, I think, is pretty safe for now, because I spend most of my time working with students, whether that's teaching undergraduates, whether that's doing outreach kind of things with school students and so on. And I like to think that what I do is kind of relies on the human element in some crucial way. So definitely I'm excited about the technological changes that I'm using in my teaching, and it's really interesting talking to colleagues in other universities and thinking about how can we use technology to improve our teaching. On the research side, I think that computers taking over from humans doing creative research is a long way off. Will it happen one day? I really don't know. I think it's a very long way off. I think there are some really interesting things going on at the moment in terms of kind of proof verification. So getting a computer to check that an argument is correct, but the human has come up, or a group of humans have come up with the argument in the first place. But that seems to me like an exciting development. I think there are all sorts of interesting things going on in machine learning and so on, all of which are being done by mathematicians in collaboration with people in other disciplines. Do I think the mathematical research is going to be taken over by machines? I think that's a really long way off. And I guess one of the things that's maybe become more clear in the public eye during the coronavirus pandemic is the role that mathematicians working with colleagues have in research in the spread of disease, and how do we manage that, and those kind of things. And I think AI is a very long way off being able to handle that.
And now again, about why study mathematics, I'm going to ask a question that is more specific to debates that are taking place in my country. So in Romania, I guess you met a lot of students that are interested in mathematics from Romania, but there are also a lot of students that you'll never meet which are not interested in mathematics. And there are a lot of heated debates in education, and parents and high school students that did not grasp the experience and thrill of mathematics routinely ask questions such as, why on earth would I need to know about matrices, integrals, or derivatives? And what would be your answer to the question? Why should people know in school about matrices, integrals, or derivatives? What are those good? Why wouldn't you learn something more practical?
It seems to me that there is a strong case for having a good grounding in lots of subjects, and clearly my agenda is maths, but I think it's important that people have a breadth of experience so that they can make decisions about what they go on and do next. How can you choose whether you're going to like this or that if you haven't experienced it? But also just things that we need to know about in order to be effective citizens. So one of the developments in the UK that's been happening, or particularly in England and Wales, I guess, in the last few years, is the creation of a subject called core maths. So students in England don't have to continue studying maths beyond the age of 16, so they can do a qualification called a GCSE, and then they could do A-levels, for example, if they're going down the A-level route in other subjects and not do any maths at all. And the idea of core maths is that it's a qualification that students can do to continue with their mathematical development, but with a slightly different focus from A-level maths, for example. And it's much more about that, being able to make sense of mathematical things in the world around us, equipping people with the skills to look at some data or draw some conclusions, or maybe just question the conclusions that are being drawn by other people. We're being told such and such, does that seem like a reasonable kind of conclusion? Those sorts of things. I guess one of the things that I'm conscious of when I'm working with young people before university is I'm not trying to persuade them all to do maths degrees. I mean, frankly, that would be a disaster because we need people to do all sorts of other subjects, but also not to go to university, to specialize and train and work in all sorts of sectors. But I would like everybody to have the opportunity to experience what I would think of as mathematics, which isn't lots of routine calculations, for example. I'm not really more excited about routine calculations than anybody else. It's about playfulness and creativity and the satisfaction of solving a problem, of seeing some ideas fit together. And it seems to me that everybody is entitled to have that experience and maybe to understand why some of their friends would like to study that further, even if they themselves don't. In the same way that I think it's really good that I got to study history at school and I got to study French at school. And those weren't things that I wanted to study further, but I feel like I'm a more useful member of society knowing a little bit about history and a little bit of French and having an understanding of why some of my colleagues did want to go and study those things further.
I mean, speaking of this playfulness of mathematical ideas, do you feel, I mean, you wrote chapter 3 entitled Who Can Study Mathematics? And I might ask potentially controversial questions, but do you think that this playfulness and this experience of mathematical beauty is within, do you think that some people are more talented at mathematics or at grasping mathematics than others? I mean, to me, it seems like an obvious truth, but you've seen countless generations of students, and perhaps you were quite surprised in your teaching experience to see that mathematics can be understood by everyone, more or less, or at least beautiful parts of it.
I think it's a really, yeah, I think the question of the role of talent in maths is a really complicated one. For me, what's important is, I guess, a couple of things. One is that I think everybody is entitled to have that playful, creative experience of mathematics. I would like everybody to have a flavor of that at whatever level. I mean, you don't have to be doing a maths degree to experience playful, creative mathematics. There are really interesting resources. There's a website called Enrich. The UK Maths Trust puts out really interesting maths problems. There are lots of organizations there that can provide interesting mathematics. There are lots of teachers doing this with 5- and 6-year-olds in school, helping their students experience playfulness and creativity in mathematics. And I think everybody is entitled to that. And I guess the other thing I would say is that I think everybody can make progress in mathematics. Is everybody going to want to devote themselves to mathematical research with the aspiration of getting a Fields Medal? Of course not, absolutely not. But I think if we think that students have a ceiling, that they have some fixed quota of mathematical capacity and that's all we can do, I think that's really damaging. There's lots of research about the impacts of students having those beliefs about themselves. If I feel like this is my capacity as a mathematician, that's problematic. It's research about teachers as well. If teachers think, well, this is all this student is going to be capable of, that also has problems. My experience of working with students across their degrees is that it's not apparent to me on day one who's going to thrive through it during their degree and who's going to find it more problematic. My experience is that students' attitude, their willingness to kind of take risks, if you like, to challenge themselves on problems, to ask for help when they need it, to take on board feedback, to explore different subjects and find the ones that they're most interested in because they're the ones they're going to want to engage with and keep studying. Those things, I think, are more important. And the students who worry about, do I have the capacity to do this? So maybe I won't try so hard because if I try, I expose myself to a possibility that I might not succeed. If I don't try, I can tell myself that my lack of success is because I didn't try. Well, that seems to me like an unhelpful attitude. So the students who get stuck in and ask for help when they need it, in my experience, make really good progress.
I mean, you mentioned this word ceiling, and since we were talking about talents and stuff, it reminded me of. Let me see if I can find something because I'm working on this right now. Do you know Douglas Hofstadter, the author of Gödel Bach? I mean, have you heard about him? Not.
I read the book a long time ago.
Right. So speaking of ceilings and talent and research level mathematics, can I read you? I found it. Can I read you a quote by Hofstadter on this area? So he says that he was extremely talented at maths at undergraduate level, and this motivated him to do actual graduate level research and become a mathematician. So he says on page 89 of I Am a Strange Loop that When I entered math graduate school at Berkeley in 1966, I had the self-image of being quite a math whiz. After all, as an undergraduate math major at Stanford, not only had I coasted through most of my courses without too much work, but I had done lots of original research, and on graduating, I was awarded the citation with distinction by the math department. I was expecting to become a mathematician and to do great things. And after a while, he said, abstraction piled on abstraction, and the further I plowed, the slower my pace and the less I grasped. Finally, after a year and a half, I recognized the situation's hopelessness, and with a flood of bitter tears and a crushing loss of self-confidence, I jettisoned my dream of myself as a mathematician and bailed out of the field forever. This hated, rigid abstraction ceiling against which I had metaphorically banged my head without any advance warning was a searingly painful, life-changing trauma. So yeah, this to me points at a huge difference between maths at university and maths done by the pros like you. So what do you think is the relationship between acing university level mathematics and being a successful mathematician?
Well, I think that doing really well at university mathematics is being a successful mathematician, because my definition of a mathematician is anybody who does mathematics, and that might be doing mathematics in school as a student or teacher or in university. And I'm not just being pedantic about words. That's something that for me is a really important thing. The way that we choose to use that language, I think, is important. I guess there are differences between studying mathematics that other people have done before and having to produce your own creative mathematics. So there may be those kind of differences between studying for a maths degree, where you are essentially learning about maths that other people have done before, and, for example, doing a PhD, where all of a sudden your job is to do your own mathematics. But even within doing a maths degree, although somebody else might have learned this maths before, when you're working on a problem, it doesn't feel like that, because you still need to come up with a solution. So I think students can still have the opportunity to try to come up with creative routes to solving a problem in whatever kind of mathematical discipline in a maths degree. But there's a difference of time scale, maybe. Maybe a student who gets stuck on a problem will spend some small number of hours on it, because then they've got a deadline coming up. Whereas somebody who's doing a PhD or who's in a research career, that might be years, in fact.
Right.
So there's different kind of experiences. I think it's really great when students who are interested in the possibility of continuing with research, for example, choose to do an undergraduate summer project to get a taste of doing research. Is this the kind of experience that I like having? It's also related to these differences between maths degrees. Some maths degrees are maybe a bit more theoretical. Some maths degrees are a bit more focused on the kind of uses of mathematics, the connections with industry, those kind of things. So again, maths degrees are not all the same.
In chapter 7 of your book, you touch upon mathematical beauty, and you quote Hardy, his famous essay, Mathematician's Apology. What do you think is the relationship between mathematics and beauty? Do you have any comments on the aesthetic dimension of mathematics?
I think this is definitely something that differs between mathematicians. I occasionally have interesting conversations with colleagues about this, and I guess what people spend their time working on varies a lot between academic mathematicians working in different areas of mathematics, let alone mathematicians working in other sectors. For me, the role of beauty is often as a kind of guide, a sort of instinct of which path shall I head down first. So if I'm working on a problem and I can think of different possible routes to a solution, but maybe these two routes feel kind of fiddly, kind of not so insightful in some way. And sometimes you have that kind of aesthetic instinct of, I'd really like this approach to work, and I'll try that one first. Does that necessarily mean I get to a solution first? No, sometimes the nice approach doesn't work out, but it sort of gives me an instinct. And also it's some of the payback, I think, that moment when you come up with an argument that feels beautiful, that is immensely satisfying, that suddenly opens the door and sheds light on what's going on. It doesn't just say, well, here's the answer to the problem, but you can also see why it's the answer, and why with hindsight that was inevitably the answer, and how that links with other things, and all of that. That for me feels like a sort of beauty. There's a sort of inevitability about it, which is really satisfying where it works out. It doesn't always work out. Do I think that always following the beautiful path leads you always to a solution? No. Do I think that beauty is the same as truth? No. There are plenty of correct arguments that aren't beautiful, but beauty for me plays a role in how I think about my subject, definitely. That may be particularly skewed by the kind of maths that I'm into, that I kind of particularly interested in, pure maths and number theory and those kind of things.
Yeah, right. So you might be biased, but do you think number theory is a more beautiful branch of mathematics than that of your colleagues?
No, I don't think I would attach beauty to a whole kind of subgenre of mathematics or not. I think it's much more about individual ideas and ideas that might crop up in several bits of maths. So yeah, no, I'm not going to claim that number theory is more beautiful than other things. I love it, but I'm not going to claim it's more beautiful than other bits of maths.
I mean, since I like logic, set theory, model theory, and the like, I deem those to be the most beautiful. I mean, I would say that, but I wouldn't defend it to death. I mean, rarely do I have the chance to speak to a number theorist that does this for a living. I mean, usually I talk to philosophers of mathematics, but someone who wrestles so intimately with numbers. I mean, what are your views? Do you have any views about numbers? Do you, how would you answer the question, what are numbers, or whether do you think they exist, or stuff like that? Do you have any views on that?
So I should be clear, I'm not working on research in number theory these days. That's not my kind of role. I spend very little of my time worrying about what numbers are, because in my world it's self-evident what they are. I live in this happily platonic world where these things exist, and I know exactly what they are and where they are, and all I have to do is try to make sense of them, which I guess is not the right thing to say on a podcast with a philosopher. So I sometimes have interesting conversations with my students who are studying maths and philosophy, who have thought more carefully about these kind of questions of what numbers are. I sometimes feel like I have a sort of applied approach in a way that I'm just trying to apply my mathematical tools to this kind of world of numbers that exists. I don't spend very much time worrying about whether they do exist. I'm happy they do. I know what 3 is. I've lived with 3 for a long time. Could I define 3 to a philosopher? Absolutely not.
Right, so it seems that you have quite a similar attitude again to what Hardy expresses in Mathematician's Apology, that this is this world, mathematical world, that is independent of us and abstract and fully determinate, and we are just discussing about what happens in this Platonic realm.
Yeah, that is my lived experience of doing mathematics. That's kind of what it feels like when I'm thinking about mathematics. I know not everybody agrees. I don't agree with Hardy about everything, by the way, but yes, I do feel like there is this nice mathematical world that I'm exploring when I'm thinking about maths.
I remember that towards the end of the book, you also have some resources like films, books, and so, for instance, you mentioned here The Man Who Knew Infinity about Ramanujan and Hardy. I mean, I actually watched one of them because of your recommendation. I watched the documentary about Andrew Wiles, the Horizon one, and that was actually quite beautiful. I mean, when I saw how much it meant to him to finally crack Fermat's last theorem, it was quite moving.
It's a fantastic documentary. So for people who haven't looked at the further reading list of my book, this is a BBC Horizon documentary from the 1997, something like that. Something like that. And Simon Singh, who made that documentary, went on to write a book about it, which people might have come across. And I love that documentary. I just think it's fantastic. I was at school when that came out, and I watched it more than once when I was at school. And I've since had the privilege of sharing it with groups of school students on events I've organized and things. And it does have a powerful effect on people, seeing this story of Andrew Wiles, who spent 7 years trying to prove Fermat's last theorem, a spectacularly famous problem. It's a fantastic documentary.
I mean, I guess this story is particularly gripping also because of the mystery of Fermat's last theorem. And you spend an entire book, you're closing the gap on another famous mathematical conjecture, namely the Twin Prime Conjecture. To be honest, I don't know the story of the twin. Does it have an interesting story like Fermat, or is it just a nice mathematical problem in itself?
Definitely has a very different kind of history, and I don't know in some ways as much about the history of the Twin Primes Conjecture because I don't know who first made it, for example. So Fermat's last theorem was prematurely named as a theorem, but was definitely asked by Fermat. I mean, had somebody asked it before, I don't know, but Fermat did definitely claim that there were no solutions to these equations. He also claimed he could prove it. And I think had Fermat just said, oh, I wonder, might it be that there are no solutions to this equation? It probably wouldn't have had the mystique of him claiming that, which when you stop and think about it is curious because he gave no evidence at all that he could back up his claim. Really, there's no reason to believe that he was correct. But somehow there's this kind of mystique about this problem because somebody claimed he could prove it, and then everybody's trying to find this lost proof in a way, rather than, well, here's a problem, I wonder whether we can solve it. So I guess that maybe helped with its the adding to the allure of this problem. I don't know how far back the Twin Primes Conjecture goes, but I think what both problems have in common is that they're not too difficult to understand. You know, a school student who's interested in maths can absolutely understand what both problems are about. Are there infinitely many pairs of prime numbers where the gap between them is 2? You don't have to have studied really any advanced mathematics at all to understand that. You just need to know what a prime number is. And it's kind of tantalizing that a problem that can be understood by a high school student, like nobody in the history of the world has been able to solve it. That's kind of extraordinary. And I guess Fermat's last theorem had that same kind of quality. I think the other striking thing about that documentary is that Andrew Wiles famously spent 7 years working on this problem or something. In secrecy. And it's kind of mind-blowing to think, what is it like to go and sit quietly in your office every day and think about this problem, particularly when you remember that the mathematician at the start of this journey doesn't know it's a 7-year journey. There is no guarantee that they will solve this problem. And that's the nature of doing research mathematics, I guess. You think about problems and there isn't a guarantee that it's going to work out. And that's something that I've had interesting conversations with school students who kind of slightly mind blown by the idea of spending such a long time grappling with a problem that's so ferociously difficult without even being sure that you're going to solve it.
Would you encourage a doctoral student to tackle an unsolved problem, or do you think that would just lead to them not obtaining their degree?
So in order to get a PhD in pure maths, essentially you have to solve an unsolved problem. That's sort of what you have to do. You have to do something that nobody has done before. But there are degrees of unsolved problem. So is it a good strategy for a PhD student to go and work on a Fermat's last theorem or a Twin Primes Conjecture or the Riemann hypothesis or something? No, absolutely not. And it's the job of the PhD supervisor, advisor to work with the student to find problems where there is a reasonable chance of success. And a lot of PhD students will work on more than one problem during the course of their PhD. They'll maybe spend a month or two on this and maybe try something else and maybe go back to the first problem occasionally, because you have a deadline and you have to have something to put in a thesis. And that's where the role of the supervisor comes in to kind of help shape that. Tackling one of these big, spectacularly famous unsolved problems is probably not a good career plan for a PhD student. Although I expect some quietly think about these things on the side when nobody's looking.
So you wrote an entire book on the Twin Prime Conjecture, and your book is called Closing the Gap. Can you please tell us why the book is called like that? What does it mean to close the gap?
So the Twin Primes Conjecture asserts that there are infinitely many pairs of primes that differ by 2. So pairs of primes where the gap between them is 2. And I guess the story that I wanted to tell was the story of the last few years of research, significant progress on this problem, not yet a solution, but significant progress, proving successively better results of the form. There are infinitely many pairs of primes where the gap is less than or equal to something. So the first kind of breakthrough in this was from Yitang Zhang, building on previous work by Goldson, Pins and Yildirim and various other people. Zhang was able to show that there are infinitely many pairs of primes that differ by at most 70 million. That feels like a really long way from 2. I mean, 70 million is not great when you're aiming for 2, except that it was the first time that anybody had proved a definite result with a finite number there. So 70 million is a lot bigger than 2, but it's a lot smaller than infinity. And then one of the reasons I wanted to tell this story is that it combines different ways of doing mathematical research. So Yitang Zhang was working kind of in isolation, I mean, building on work of previous mathematicians, but essentially working by himself and then making this spectacular announcement. But building on that, there was then a collaborative online project. So this idea of collaborative online projects, mathematical research projects, have been started by a mathematician called Tim Gowers a few years earlier via his blog. He called it Polymath. There's a joke in that. And so another mathematician, Terry Tao, said, well, why don't we have a polymath project working on this work on bounded gaps between primes? Can we make this 70 million closer to 2 and also understand a bit more about what Zhang did? So through the course of 2013, 2014 and so on, this number kind of got smaller and smaller. So that gap is not down to 2 yet, but there's been loads of progress.
What's the number?
So the polymath project, and then some more work by James Maynard and Terry Tao, and then more work by Polymath got it down to 246. If you allow yourself to assume various unproven conjectures, then that number would get down to something much smaller, like 12 or maybe 6. But
oh, really?
That's depending on unproven conjectures. I mean, before Zhang, Goldson, Pins and Yildirim had got this sort of rather small number, but depending on another conjecture that seems very hard to prove. So I like this story for the sort of solitary mathematician, which is maybe the figure we recognize historically. That's maybe how we think of research happening, but also this very democratic, online, collaborative, shared experience. It's all in public, it's on blogs, it's on wikis. You can go and Google polymath bounded gaps between primes. You can see all of the information about it. So doing research in public rather than a mathematician or a small group of mathematicians with a whiteboard or with a piece of paper that nobody gets to see. So it's really interesting insight into the process of doing mathematical research, as well as a story of a famous unsolved problem.
So if Polymath manages to eventually crack the Twin Prime Conjecture, this will give a wholly different story than the one of Andrew Wiles, right? Because it's a collaborative entity that works out in the open compared to someone working in solitude for 7 years and with uncertain.
Right, it's a completely different way of approaching mathematics. And I guess in other disciplines, really large-scale collaborations are well established. And I mean, open source computer software or the Human Genome Project or sort of high energy physics like CERN and so on, you get research papers with very large numbers of names or very large numbers of people in a team contributing. Pure mathematics historically hasn't worked like that. Pure maths historically, a paper with 6 names on it, that's a big collaboration. So this polymath is a new way of working, and it's kind of an experiment, I guess, to see what's possible via this route. What kind of problems lend themselves? What ground rules do you need to have in place to establish the right kind of working dynamic for a big collaboration on a pure maths problem?
And it's also it's interestingly different than what Andrew Wiles did, because with the Polymath project, you can actually measure your progress because you're squeezing the gap from the initial result, then you hope to get to 2. I guess Wiles did not have this equivalent of getting closer to cracking the Taniyama-Shimura conjecture. So
I guess it's a feature of the bounded gaps between primes that you can kind of quantify progress in that way. And indeed, there still is a league table on a wiki recording. You know, people could come along and say, well, I think I can get this number. Here's a link to the blog post or the web page or whatever, where you can read about how I've got there. So the problem had this quality that potentially you could have the world record on this problem, sort of publicly. You could come along and claim that, which I guess made it very attractive for this large scale collaboration. I think that's very unusual in research. It's very unusual to be able to quantify how close you've got. And I mean, in some ways, it's not a very accurate quantification, because getting from 70 million to 50 million was a lot easier than getting from 2 million to 2 or something, right? There's some of these gaps are harder than others, but it certainly attracts people's attention, and I guess it encourages people to join in. Normally, it's very hard to tell whether people are making progress on a research problem. It's very hard to tell whether you're making progress on your own research problem.
I mean, just crossed my mind. I don't know whether this is an interesting question or not, but because you're actually getting towards zero in the towards two in the squeezing the gap process, instead of going to infinity through the natural numbers. Do you think that having seen the gap getting more and more squeezed offers you inductive support from believing that the twin prime conjecture is actually true? Usually the gold standard of mathematical certainty is proof, but would you bet money on the fact that the twin prime conjecture is true based on what you've seen so far?
I'm not a betting person. I do think the twin primes conjecture is true, but not to do with this closing the gap business. So there are sort of two reasons for thinking it's true. One is that you can ask your computer to go and find very large examples of twin primes, which is not a proof of anything, because your computer comes back and gives you two enormous prime numbers that differ by two. Well, there's always a risk that that's the last, but the fact that computers can find these things is sort of encouraging. A better reason is that you can kind of model the prime numbers. So it's not random whether or not a number is prime, and a number just is prime or isn't prime, but you can kind of model the primes as though you tossed a coin for each number, and the coin determines, heads it's prime, tails it's not prime. The primes aren't spread sort of 50-50 prime, not prime, so you need a biased coin for this, but you can do this. You can carefully set up, and that doesn't tell you anything for sure about the primes, but it's a sort of what we would call a heuristic. It enables you to make predictions, and you can actually use this heuristic approach to predict how many pairs of twin primes you would expect, up to 1 million or 1 billion or 1 billion or whatever. You can write down a formula for, I guess there should be this many pairs of twin primes, and then you can compare against the computer data, and then the computer data is kind of slightly more useful than just here's a big pair of twin primes, because you could, and this is an astonishingly good prediction. I mean, astonishingly good. And the prediction, this formula definitely predicts that there are infinitely many twin primes. It predicts a lot more than that. So that's not a proof of anything. That does not meet the kind of mathematical threshold for proof. The twin primes conjecture remains unproven, but it's very compelling reason for mathematicians to believe the twin primes conjecture.
Well, now that I'm looking at the time, I realize that I kept you more than what I promised. So on this note, I want to say that it was great having this conversation with you. So thanks again for being my guest and for writing great books for young mathematicians.
Thank you for inviting me.
I wish you a great day, and thanks again.
Bye-bye.